Welcome to our next lecture in this series on condensed matter theory. In this lecture I want to talk about the specific heat of metals as we observe it or calculate it within the Sommerfeld model. And the experimental observation for the specific heat is such that as a function of temperature from 0 to something small, let's say 10 Kelvin, the specific heat is basically a linear behavior. So Cv is alpha times T. And we've also seen that in the Drude model, Cv should be K Boltzmann, 3/2 K Boltzmann, a constant. So how can we explain this and how can we get from this constant that you get for a free electron gas or a kinetic gas theory to something that goes to zero at zero temperature, especially because the specific heat tells you how many ways you have to excite your system at that temperature. And for a metal there must be a way to excite that system because otherwise you wouldn't have conductance. So the specific heat is given as the derivative of the energy with respect to temperature at constant volume so that we don't do work. And we can calculate the total energy in our system by the integral over the number of states that we have with a certain energy times the energy of that state times the occupation that we have in the Fermi-Dirac distribution at that energy. Now, in order to evaluate this integral, we can use the Sommerfeld expansion, and we will do that. And in the lecture I showed you the Sommerfeld expansion without this additional energy. However, if you look at those steps, you will see that you can very simple add this additional energy. We'll do a Taylor series expansion at some point, and then just the orders of that Taylor series expansion will change. That might change a little bit the prefactors, but otherwise everything is the same. So I will not redo that Sommerfeld expansion, but we'll just come to the answer. And the energy is then given by the energy at T is 0, which is the first term in the Sommerfeld expansion where you integrate up to the Fermi energy, plus, and then we have the correction, pi square over 6, pi square comes from the zeta function, and then K Boltzmann T squared times the densities of states at the Fermi energy. And we can then of course calculate the specific heat as the derivative, which then becomes pi square over 3 K Boltzmann square T times the densities of states and the Fermi energy. And you see that very nicely, indeed, the specific heat is linearly proportional to temperature. We can actually get a physical understanding and also do a simple approximation to get this linear behavior. And we can explain why the specific heat goes to 0. For that we look again at the Fermi surface. And we have a Fermi surface where states inside are occupied and states outside are empty. We can now look at two different scattering processes. An electron here might scatter to an electron there. That process is forbidden, because when this electron wants to move there, it's wanting to go to a state that is already occupied, so this is forbidden. The only excitations that are allowed are excitations where an electron from inside the Fermi surface scatters to something outside the Fermi surface. That of course costs you an energy that is related to the change in the length of the wave vector. Now, if you want to make excitations at zero energy, you cannot do that inside the volume of the Fermi sphere, but you can only do that at the Fermi surface. Now, the ratio of electrons at the Fermi surface to the number of electrons inside the Fermi sphere is 0. So indeed, you will find that the specific heat will scale down to 0. And we can actually even explain the linear behavior, because at finite temperature you are able to now make excitations from inside to outside the Fermi sphere, where we do not have the surface that we have to look at, but we can look at a shell that has a thickness of K-Boltzmann T. For that we can have a look at the Fermi-Dirac distribution at zero temperature. This is just 1 below the Fermi energy and 0 above, and the number of electrons that can excite are given by this line, which is 0 compared to the total numbers that I have. However, if I look at higher temperatures, then I have excitations and therefore I'm now able to make scattering. An electron here can scatter there, or an electron here can scatter there, and those are all allowed processes. Of course, well, it should scatter there, outside, in the unoccupied states. We can now also estimate what the change in energy is, and therefore what the specific heat is. We have excitations in a range that is proportional to K-Boltzmann T. The excitation energy is the number of states that we have at the Fermi energy times the excitation energy, and that's of course the energy of a single excitation, but we have K-Boltzmann T of such kind of excitations because that's the number of electrons that participate. So the total energy is the EF times K-Boltzmann T squared, and therefore the specific heat should be proportional to the derivative with respect to T of that, which is 2 densities of states K-Boltzmann square T. If we now compare this simple consideration with the result we get from the Sommerfeld model, then you see that you're only off by a factor of pi squared divided by 6. And that is then just, well, you're not looking at a range of K-Boltzmann T, but you should look at a range of pi squared over 6 K-Boltzmann T, in which you can make these excitations. But that's order unity correct. You at least get the correct behavior both on the densities of states as well as the temperature in there. So indeed we find that in quantum mechanics the specific heat of a metal goes to 0 when you go to 0 temperature, because you cannot make excitations from electrons that stay inside the Fermi sphere because of the Pauli principle. These electrons still contribute to the conductivity, because when you do the conductivity you shift the entire Fermi sphere, but they do no longer contribute to the specific heat because they're blocked by the Pauli principle. Which is a very powerful experimental finding to show you that you need something along the lines of Pauli-Dirac, Fermi-Dirac statistics or the Pauli principle. And therefore you need something in the form of quantum mechanics, where each state can only be occupied by one particle. Thank you very much. We see each other in the next video. Stay healthy.